All right. Здравствуйте, друзья. Let's get started here. So we're going to talk a little bit about strings, and I never thought 20 years after Java was created I'd be doing a talk on how strings work, but this can run fast like Java and other statically typed languages. Integrating with native code. There's a lot of C libraries that Ruby developers expect to call, not the least of which is most of the POSIX calls that are available. They expect to behave like they would if you were writing C or writing Ruby, so we need to be able to simulate or call those same functions. My talk later tomorrow, I think the last talk tomorrow, is actually going to talk a little bit about how we're integrating with native code and how you as Java developers can take advantage of that. Process management comes along with this. Ruby, with its roots as a scripting language, has been used to do a lot of process control, starting little processes, sending them commands, receiving output, all of which are a little cumbersome to do on Java with the process APIs. They don't allow things to be interactive. I'll also talk about how we're doing that tomorrow and how you can control processes better from Java. But today what we'll be talking about is the interesting challenge of supporting many different string encodings on a platform that only has one, Java, with its UTF-16. So let's jump right into that then. Okay, so today we'll talk a little bit about what makes up a string, what it actually is composed of, what sort of encodings there are out in the world. Of course, you folks here in Russia have your own text encodings that you use for things, and you've had to deal with the translations and challenges of dealing with encodings around the world. And we'll talk about some of those encodings and why this problem may not ever go away. And then we'll talk about a couple libraries. The key ones, JCodings, a Java library you can use to manage strings in their original encodings. Rather than pulling them into Java as actual Java characters, you can leave them in your native encoding and still work with them correctly. And then if you're going to be working with strings, that brings along regular expressions. And we have a regular expression library that works against raw bytes in any encoding, so you don't have to turn them into Java strings to do regular expression matching. And then we'll wrap up and have some examples and discussion. Okay, so let's talk first about strings and encodings. So what is a string? Well, a string is a finite sequence of characters, according to Wikipedia. So it's a finite number of characters in a particular order, a sequence. Usually this is represented as an array. As in Java, it's an array of characters. So usually that's a contiguous space in memory where we have all of the characters lined up one right after the other. But there are other representations. Many folks have experimented with something called ropes, where you have a tree that has a bunch of small arrays in it. And the actual string that you get out of it is basically made from walking that tree and composing those pieces. It allows you to break it apart, reassemble it more efficiently than copying all the characters every time. In other languages like Erlang, it may actually be a list. And Erlang is not particularly legendary for having high-performance strings, mostly because they are immutable lists, just like any other collection. And I mentioned mutability and immutability. Most computer language creators now agree that immutable strings are generally the right thing to do. The cost of creating new strings is usually much smaller than the hassle of synchronizing on a mutable string and making sure other people aren't modifying it. But many languages have mutable strings or both as options. And then if we have a sequence of characters, we want to be able to access them in some order. We may be able to want to jump into the middle of the string. And different representations may have constant access time, or you may have to search through the string to find the nth character. And that can play very heavily into performance. So what is a character then, if we're talking about strings? Well, for most non-programmers, what they see as a character is the glyph they see on the screen, the actual shape of a character. This isn't really interesting for us because, as developers, we know there's a native representation, and a particular character may have many different glyphs in different fonts and locales. If you're a linguist, you might think about characters in terms of graphemes, which would be the smallest piece of a character that you can break it down to. For all of us, it would be a letter in one of our alphabets, perhaps with diacritical marks as a separate part of it. In some of the Asian languages, such as Chinese, a grapheme would be individual radicals in a Hanzi or a kanji character. But for programmers, what we think about as a character is basically a combination of those graphemes to mean a single entity. And again, not tied to a specific glyph. We're going to have different fonts and different locales that will render these characters in different ways. So early representations were somewhat limited in scope. People did encodings that only represented the languages they were interested in. And so we ended up with a lot of incompatible encodings. And we'll talk about what sort of problems that has led to over time. And because this is largely focused on only one language, I'm focusing on my language at a particular time, these are frequently single locale. So sending character data across language boundaries or country boundaries runs into lots of problems. So first of all, we'll talk about ASCII, which is one of the earliest ones. The American Standard Code for Information Interchange. And of course, American there gives away a lot about this. This is a focus on English characters, not even the variant characters that are in some of the European languages, but very specifically what's in British or American English. This has been around for a long time. First published in 1963, largely unchanged in the past 30, 40 years. And this is actually a 7-bit encoding. Many people think of ASCII as being an 8-bit encoding, but only the first, the 7 bits, the low 7 bits of this are used. But since we don't really want to work with 7 bits at a time, this has kind of been the largest contributor to why we have 8 bits in a byte. We wanted to be able to represent all numbers, all characters in a particular language, and some control codes. Big reason why bytes are 8 bits today. As I mentioned, this is largely unchanged since 1977. There have been minor revisions over time. And many modern encodings had to be compatible with this. So the fact that this kind of got first out of the gate for representing characters meant that all future encodings were expected to, or weighed in terms of their compatibility with ASCII. All right, there's our typical ASCII chart. Nothing surprising there. Everyone's had a look at those before. But obviously, very focused on English here. So we needed something better than this if we're going to represent all the languages in the world. And so ISO 8859-* came around to try and standardize the high bit of the byte that we're using for a character across many other languages. So we're going to use those high 128 values to add an additional alphabet. We'll have the English alphabet along with some other that we can represent at the same time. So this covers Latin variants and non-Latin languages, such as Cyrillic and Eastern European texts. Languages like Thai that have an alphabet that can fit into 128 characters. This is not really room enough for most of the Asian languages. Chinese, Japanese, Korean specifically have no way of representing their entire alphabets, much less all of their characters, in only 8 bits. So the picture here is ISO 8859-5, which was an early attempt to represent the Cyrillic alphabet. Unfortunately, it was not able to represent all the variants of Cyrillic languages, so it was largely superseded by KOI-R, KOI-U for Ukrainian, and these days Windows 1251 that is used on most systems. So now we've largely just covered single byte encodings, which only work if you have an alphabet. So ASCII is just Latin characters. That's easy enough to fit into 7 bits. The ISO encodings are basically Latin characters plus some other character set. Now an obvious problem pops up. What if we want to represent another one? What if we want to represent Latin and 2 different alphabets? Well, it's not really easy to do, maybe not even possible with a single byte encoding. And then, of course, we get to languages that have way more than 255 or 128 characters, like Chinese, Japanese, Korean, and other Asian languages that may potentially need 1,000 or tens of thousands of positions to represent all of their characters. And then we go on from there. We want to be able to represent archaic languages that don't exist anymore. We want to be able to represent symbols, pictographs, shapes. None of these things can fit. We're way beyond the 8-bit range here. And of course, with only a single byte encoding and everybody using their own version of it, you end up with really bad behavior when you pick the wrong encoding. Folks have probably seen text like this in the room. This is actually Windows 1251 representation of Cyrillic, the first few lines of Book 1 of War and Peace. But my Vim interpreted this to be ISO 8859-1, comes out completely garbled and impossible to read. These are the sort of problems we have in a single byte world when we're trying to work across languages. All right, so what do? We don't have enough room in 1 byte. We'll move on to multi-byte encodings. And of course, lots of pain results from this as well. We've got multiple incompatible representations. Some of the early multi-byte encodings are not compatible with later ones. Obviously, there's incompatibilities or challenges integrating with the ASCII and ISO 8859 encodings. We now need to use some marker bytes to know that we're not in the original 100 and... Okie dokie. Well, I'll just keep talking and tell you what it says. So problems integrating with the single byte encodings because they consumed all of that byte space, and we're in rough shape when we have to represent more characters. So if only bytes had actually been 16 bits, maybe we wouldn't have as much problem. We'd be able to represent far more characters and maybe be okay. All right. Now we're moving on to Chinese, Japanese, and Korean as a more specific example. So Japanese, for example, has two alphabets, hiragana and katakana. Both of those have 46 characters. Obviously, we're pushing the bounds of what we can fit even into the high bits of an ISO 8859 range, a byte range. The characters that they use, the pictograph characters, Hanza, kanji, these are thousands of characters, maybe tens of thousands or hundreds of thousands in some languages. Yes, so maybe the character encodings in the projector aren't working great. Okay, so Hanza and kanji from Japanese and Chinese, thousands of characters. I think in Chinese there's a representation of, let's see, oh, we're back? Hey, over 100,000 different characters in Chinese. Way beyond a byte, potentially beyond 2 bytes of representation to even fit all of those in there. So we've got a problem here. Luckily, only about 2,000 to 7,000 of these characters in Chinese and Japanese are considered mainstream, considered to be the characters used on a daily basis. So we do have a possibility to fit it into a smaller size for our characters. And multiple encodings that are used by Chinese and Japanese languages in the past are still in use today. They're not necessarily using Unicode. They're not necessarily using the current standards for language representation. So again, we have ISO 8859 encodings, we have Asian language encodings, and they're not going away. Okay. All right. So we'll move on and talk about Unicode, since I can't show you any Unicode. So Unicode really is kind of the first attempt to create one encoding to rule them all. We want to have a single representation of all characters in all languages and not have this issue of translating texts across boundaries. So Unicode actually started with its first draft in 1988, Unicode 88. And this started out with 16-bit characters. Like I mentioned, maybe if we'd started with 16-bit initially, we wouldn't have as many problems. Now really only 14 bits of this were usable, because others were used for controls, character flow direction, script direction, and so on. And as a result, there was only about 16,000 characters that we could represent in Unicode 88, or in UCS2 as it was called later on. And then at the time, only contemporary in-use languages were considered. So archaic languages weren't in there. Symbols, pictographs, fictional languages also did not show up in here. And then in about 1991, Unicode 1.0 followed up and started to codify some of this more concretely. So in 1991, along with Unicode 1.0, we started to move into ISO 10646, which was a representation used to this day of all characters in all languages. Basically a giant table of numbers mapping to the characters. The code points that we see in Java, mentioned from time to time, that's from this standard. Developed in tandem with Unicode since 1991, and it only includes the actual characters. It doesn't do anything with the flow of code, the flow of text, if it's left to right or right to left. It doesn't do anything with combining marks, taking 2 characters and turning them into a single one. All of that is on the Unicode side. This just defines the individual characters and their code points. And when Java 1.0 came out in 95, 96 or so, UCS2, the Unified Coding Standard, for 2 bytes, was used as the representation of a Java string. Still not live, okay. So beyond that, we have Unicode 2.0. Unicode 2.0 realized, all right, it's not going to be enough for us to do just 14,000 characters, especially for these Asian languages that may have tens of thousands of characters that they need to represent. So we had this thing introduced called UTF-16. UCS2 became UTF-16, and we have to now represent some characters as multiple UTF-16 characters. Kind of getting to be a mess at that point. Unicode continues to evolve to this day. 1997 or so, we introduced some musical symbols into Unicode. 1998, some archaic languages like Egyptian hieroglyphics. And then, of course, today we have the modern hieroglyphics in the form of emojis. So, we have a problem here. Maybe we should just turn this screen around. Single byte encodings are more efficient, but you can only represent 2 alphabets at a time. That's not great. This is a global internet that we have, and we need to be able to represent more than 1 language, definitely more than 2 languages too. If you pick the wrong encoding, as we saw, you get garbled text. No, you can't read anything. So you have to know what that original text encoding was, or you're going to get some nonsense out of it. And there are no clear ways to guarantee that you guess the correct encoding. Things are happening. Things are happening. So multi-byte encodings are more complete, but it's only efficient for the English alphabet. That's the only area in UTF-8 that gets a single byte per character. So unfortunately, all other languages get forced into multi-bytes. And multi-byte is just kind of sucks. It's much more difficult to search. You may have more than 1 byte per character. You may have a variable number of bytes per character. This is a problem for all of the different languages that are not just using the English alphabet. There's also a problem called Han unification. The Han unification problem stemmed from the Chinese, Japanese, and Korean kanji, Hanzi characters, being unified into a single set. That sounds great for us that are not Asian language speakers, but it turns out they had different meanings for these characters and didn't like that their character in Chinese might be represented as the same completely different meaning in Japanese. This is a big reason why the Asian countries that use kanji don't actually adopt Unicode and still use their own historical encodings. And so we may never solve this. Everybody wants to use their own encoding. Everybody wants to have an efficient byte representation. So we live in a world that's going to be multi-encoding, and I don't see that going away anytime soon. Okay. So now we'll talk about Java. We've got the history lesson over. We'll get into some of the more practical details here. So of course, Java's string is represented as a character array and a length. Fairly simple. And as I mentioned in the beginning, this character array was UCS2. 2 bytes for each character, and that was the entire range of characters that you had available to you. Now, of course, that was pretty good for most of the Western alphabets, but most of the alphabets other than English would basically waste a byte. So you were taking up 2 bytes for every character when you could be using 1, and some of the Asian languages with their characters were not large enough. Java also had to adapt as UCS2 turned into UTF-16. And so what we have to this day is UTF-16 characters, where it may be 16 bits for a given character, or it may be multiple chunks of 16 bits. This has been around for a long time, and this is part of the standard. The original Java specification said characters shall always be 16 bits wide. As a result, there's no way that we could have gone to, say, a 32-bit representation when it turned out 16 bits wasn't enough. We're stuck with this. We have to kind of work around some of the flaws of UTF-16. What are these problems with UTF-16? So, first of all, since most languages and most regions like to use their own single byte encoding, we now have to be constantly translating back and forth between the encoding on the operating system and Java's UTF-16. And we have to go back out again. And the funny thing about this is very frequently we are decoding from UTF-8, a Unicode encoding, to UTF-16, a Unicode encoding, back to UTF-8, a Unicode encoding. Wasting all of this time in the middle just because Java, unfortunately, chose a representation that kind of became a legacy of Unicode. This is also a large part of the performance gap with C and C++. Constantly transcoding strings back and forth during I/O makes it almost impossible for us to compete with C++. If you want to do fast character I/O, there's no way you can actually use a Java string. Sad but true. And of course, the ASCII range, which is always represented as 16 bits, is constantly wasting 1 byte. It doesn't use the other byte at all, not even as a character mark to indicate that it's a high order language. This has been improved somewhat in Java 9. Folks like Mr. Shipolev have worked to compact at least 7-bit ASCII strings down and represent them as single byte ranges. But there's still more that we need to do here. Most languages are still fairly wasteful in memory when you pull up UTF-16 characters. We also have no options for an alternative representation. If you want to use Java and you want to use any API that uses Java strings, you're stuck with UTF-16, and there's no way to work around that. In JRuby's case, a peculiar situation is that we want to sometimes embed different encoded strings or perhaps a big num, a big integer, in a class file. Well, class files only allow you to embed numbers and UTF-16 characters. We have no way of representing anything else that's just a binary range of bytes. So we have to kind of pack it in there somehow. So this kind of ends up being the worst of all worlds. Yes, we get constant access for any individual character in the string, but we're wasting a lot of space and we're wasting a lot of performance reading and writing strings to the system. So, I work in Ruby, I work on JRuby, and we'll take a look, we'll have a discussion about what Ruby actually does here. So in Ruby, rather than representing a string as always being Unicode or always being UTF-16, each string has its own encoding. So a string is a byte array, a length, and an encoding. It's also knows it, so each string can have its own encoding, but more importantly, each string knows its own encoding. As you pass these strings around, it's not just an opaque byte array. You know exactly which encoding it's in, so you're never mixing up different languages. And as a result, strings have operations for doing both byte-level operations and character-level operations. You could split a string up that may contain binary data into individual bytes, or you can find all of the characters there. Now this sounds complicated, and it kind of is. We spent years implementing this whole process in JRuby, but it does work. It allows you to basically take character data from the system, pull it into a Ruby implementation, like JRuby, and work with the characters in their original encoding. You don't have to decode, you don't have the transcoding overhead at all, and you have the most compact implementation, or the most compact representation in memory. So string I/O comes out nearly free. JRuby can actually beat Java for doing character data in and out for I/O, simply because we don't have that overhead of UTF-16 characters. This is really impossible to match with fixed encoding strings. So then that brings us to JRuby. As I mentioned, we opted to go for the Ruby way. Originally, we tried to implement Ruby strings using Java's strings, using Java's character, but it just ran into too many problems. Not only did we have character sets that couldn't round trip completely through UTF-16, but we had no way to represent binary data efficiently. There's no way to have a string that represents binary without creating a garbage string. So we had to rewrite all of the character logic, implement our own string, implement our own regular expression engine, and luckily we've managed to make this all work over the years. Like I say, it was a lot of work. I think we fixed our last major issues here last year, and the original start of this process in Ruby was probably about 6 years ago. So a lot of work that it took to get here. The other downside to this is that interop with Java became a bit harder. We have a much richer string, a better representation of a string than what we can do on Java. Anytime we need to call a Java API, we have to do a transcode and then back again. In practice, this doesn't turn out too bad. You can work with Java strings directly in Ruby, so most of the time that overhead is not too bad. Okay, now the good news about this is that it actually does work. And I'm not expecting any of you need to use JRuby to do this. We have pulled these features out as plain old Java libraries that you can use. And I would like for anybody to try this. If you're dealing with character encoding, hopefully this will help solve some problems for you. So one of the libraries that's sort of a support library for this, not really related to character encodings, is called bytelist. It may be the only Maven project out there with a single Java class file in it. Bytelist is essentially string buffer for byte arrays. Allows you to concatenate them, append them, split them, add to them, and it'll grow efficiently for you behind the scenes. All of the things that you probably wanted to do with a byte array at times, but couldn't do with, for example, byte buffer, which has a fixed size. This also provides an unsafe direct access to that byte array. So, for example, you can take an array of bytes, put it into a byte list, use these different features against it, and then access them directly. Not possible to do with string buffer, kind of possible to do with byte buffer, but there's other problems there, of course. We are expanding this to also include all of the character logic from the other libraries I'll show. So ideally, in the future, you could just pull in a byte list, wrap it around your byte array, and be able to walk all the characters. But the other libraries that I have here will give a little bit more examples of doing that directly. Help wanted here. If you could see it, there is a URL for the GitHub project, but it's under jruby/bytelist. And if you're interested in having a string buffer for byte arrays, help us clean up this API, see if we can make it look a little bit better. All right, so moving on from bytelist to one of the actual libraries that are dealing with encodings, J-codings. So J-codings basically encapsulates all of the logic of translating from one character encoding to another. How to walk the characters in that language, what code points they... we're back, hey, just in time. All right, see, we're already fixing things with J-codings. So, allows you to decode and encode characters from one character set to another. And this is back and forth to a code point, a value, and then to a byte array, not having to force you into an intermediate form like a UTF-16 or UTF-32. You can work with characters in their original representations. Of course, character walking. Many of these encodings have variable length. So you need a library that says, okay, this is going to be a 2-byte character, this is going to be a 3-byte character, moving your way through the string correctly. It also does some validation. There may be invalid characters in that sequence. J-codings can tell you where exactly there's a bad character in the sequence and help you translate it to something that makes sense. And now I mentioned that you can do encoding from code points to bytes and back again. It also supports transcoding. You can take an array of bytes in, for example, Windows 1251 and translate it directly into UTF-8, rather than passing it through UTF-16 as an intermediate. That skips a whole lot of overhead on the Java side, especially since usually we're not dealing with a UTF-16 world. Usually we're dealing with one of the single byte encodings, or with, for example, Windows 1251, another single byte encoding that's not part of the ISO standard. Here are Maven coordinates for this, if you want to pull it down. And again, the URL for this one under GitHub. All right, so encoding support that we have in here. Lots of different encodings. Of course, all of the UTF encodings are in here, with all the endians that are available. ISO 8859-* all available in here. And even Java doesn't support all of these. I have a couple patches that I need to get submitted to OpenJDK to add, for example, ISO 8859-11, ISO 8859-15, I think. So we're even ahead of Java here as far as the encodings that we support. And then, of course, all the Asian languages, their encodings that there's... Oh, yeah, there we go. Of course, all of the Asian languages. In Japanese, generally the JIS encodings, Japanese Industrial Standard, still used to this day for representing most Japanese text. It's a multi-byte encoding, incompatible with Unicode. You can work with it directly. EUCJP, another Japanese encoding that is used a little bit less. GB, which is the Guobiao set of encodings for mainland China, a standard required by the government for all software sold in the People's Republic of China. You must support the GB encodings along with whatever else. And the Big Five encodings, which are representing traditional characters in Taiwan, so named for the Big Five companies that came up with it originally. And then, of course, all the IBM and Windows code pages. I mentioned Windows 1251, for example. There's room to grow here. I don't expect that the flow of new encoding systems is ever going to end. It should be easy enough for us to add additional encodings here, as long as they conform to at least the unified character set code point mapping. Okay, so some basics of using this here. Wait, we went back. So here's a quick, simple example. We have a string with some non-English characters in it there. In this case, we're just going to look at the UTF-8 version of that. So we've got our array length, which of course is not the character length. There's 7 bytes here for the 5 characters. If we use str length, we can actually get the character length of a given byte array, given a particular encoding. Here we can also see with the length call what the length of a particular character is. So if we look at the first U there, we know that it now has 2 bytes, and we know to walk 2 bytes forward to get to the next character. Similarly, we can take that range of bytes, starting at 1 and going until 3, to turn it into the code point that it's represented. You'll notice here I'm comparing it with a simple Java character. The code point value actually comes right back out as what we'd expect as an int value for a character. That really is the code point in Java. So I mentioned transcoding. This is one of the cooler features of J-codings, being able to take a byte array to a byte array without any intermediate form. We don't have to read it in to UTF-16 characters and then encode it back out again into bytes. We can go directly. This is a pausable transcoder, which means that at any point along the way, if there's not enough character data, we can stop it and resume when the characters are available again. And it keeps track of where it is in that process. If we were partway through a sequence of characters, it knows how to continue. There's a huge inner loop here that's a very interesting code if you want to see nightmarish C ports. This thing had nested switches, it had loops, and on top of the nested switches and loops, it had arbitrary go-tos jumping around in that code. You can imagine how fun that was to convert to Java, but it does work pretty well. Kind of a state machine that was built to support it in J-codings. And a far better performance than taking byte array to character array and back again. If you want to do a lot of text processing that's converting characters from one encoding to another, this is going to be the fastest way to do it, for sure. I would say this is comparable performance to charset or charset encoder decoder, but only one stage of that. If you wanted to go from Windows 12.51 to UTF-8 in Java, you've got 2 steps. We only have 1, so we generally win. Okay, an example of using the transcoder. So in this case, we're taking UTF-8 bytes and turning them into UTF-16 on the wire. We've got our UTF-8 foo. We create a new byte array to hold the UTF-16 size of bytes. Down here with the econv.convert, we pass in the source bytes, a pointer, so we know how far we got through those bytes in the original encoding process. We're telling it there's 3 bytes there. And then we give it a destination byte array. It does the translation for us and puts the number of characters in our out pointer. In the end, we get what we expect. We have the raw UTF-16 bytes, and we didn't have to turn it into Java characters. We can now write this back out to the wire directly. So there are some bonus features in J-codings. It does some carriage return line feed negotiation as well. So you can decide that you want all carriage returns and line feeds to be Windows style, carriage return line feed, when you read them in off of a wire. And it'll turn it into that and give you the proper representation. Or, as is more common, take all of the carriage return line feeds in any combination and turn them into a single new line character. We can also do XML entity replacement for very simple things. So if you have characters that are not allowed to be represented in XML text, for example, less than, greater than, and so on, you can specify that the transcoder should also introduce the character references, the appropriate things for those characters. And in addition, for higher-end Unicode characters that need to be represented specially in XML or HTML, it can do that translation for you. It also supports multi-stage transcoding. Some character encodings don't have a direct mapping from one to the other. So when there's no direct translation between 2 encodings, J-codings will automatically do a multiple stage translation for you. It's not particularly common, but if you need to go from ShiftGIS SoftBank to UTF-8 SoftBank to UTF-8 to CP 51932 to code page 50220, something I'm sure we've all had to do. It's just such a problem. You can do it and it'll automatically figure out the sequence of encodings necessary to get the characters from one to another. And then, as I mentioned, that the entity replacement in XML and the carriage return line feed actually basically just acts as an additional stage in the transcoder. So here's an example of the universal new line feature. So here we see we're opening a transcoder that's not actually changing any character encodings, but we want to change all of the new lines in this string. So we have our foo \n /r/n bar that we want to make all just new lines in a representation. We pass it into the converter, same code as we saw before, and it translates any of those so they have the right new line. Similarly, XML attributes and character references. Here we have some characters that are not legal to represent in Unicode, such as a less than or a greater than. We have some embedded Unicode characters. They all get translated properly, so you can stick this into an XML or HTML document and it'll render properly. Okay. So performance-wise, it is kind of difficult to whoops. Oh, that one all came up at once. So performance-wise, it's kind of difficult to compare this with what we have in Java. Java always has to go through UTF-16, so any sort of byte-to-byte transcoding, Java loses, clearly. If you're only doing one stage of that, we're generally about the same performance as doing a char set, so you're not going to lose any overhead in that case. And it's similar to that one stage, either decoding or encoding, if you're using those. For us, it has not been a bottleneck. It works pretty well. Doing the character encoding translation happens quite a bit in Ruby, as you might imagine, so I don't expect it'll be too much of a problem for any of you. Users of this, Facebook has a project called Presto, which is a query engine for distributed big data. In order to make that perform well on top of a JVM, they use J-coding, so they don't have to decode into a character array. They're able to read in the bytes from some large store of data without making any modifications to it, without transcoding it, do their querying, do their searching over that string, and then pass it right back out as a result. Almost impossible to get the performance that they have now if they were using Java strings. Of course, the Ruby implementations on the JVM use these features and use these libraries. JRuby, the project I work on, and Truffle Ruby, another one that Oracle's currently working on. And then several of the Ruby-related IDEs and tools use these libraries. Even though they're written in Java, they still need to work with encoded Ruby text and Ruby source code, and so they use our libraries to make things work. Okay, so the last library I want to cover, Joni. So Joni, which stands for J Oniguruma, it's a port of the Oniguruma library from C Ruby. This is a C implementation of regular expression engine that allows you to have any arbitrary encoding for the bytes that you match. It's pretty magical, a regular expression engine that does not force a particular encoding upon you. There is some divergence from C Ruby, but we largely have been tracking their features. So with Joni, you can actually do regular expression matches directly against bytes in their original encoding. Anybody who's had to match against a large piece of text knows the pain of having to read it in all as UTF-16 characters, do your matching, and then write it back out, and hopefully match up where your character offsets are in there. This is based on J-coding, so it supports the full range of encodings that are in J-codings. And even better, it has pluggable regular expression grammars. So you folks may be interested primarily in the Java regular expression features, but Ruby, JavaScript, and others have many additional cool features for representing regular expressions. You can actually plug these grammars in and use them directly against a byte array. Another cool feature of this, it's stackless. The Java-util regex package has issues with large content because sometimes certain regular expressions will recurse. It's possible to actually blow the stack just by feeding a Java regular expression engine enough data. Some of you may have run into this. We certainly did in the early days of working on JRuby. Maven coordinates and GitHub URL for that one. So I mentioned Java-util regex. So the obvious big difference here is we're working directly against raw bytes. If you use Java-util regex, you've got to turn everything into characters. So there's a downside already. I mentioned the recursing problem. In particular, alternations where you have an A or B in a regular expression. Java util regex will recurse for certain versions of that. And as a result, if you feed it enough content, you blow the stack and there's no way to do the match at all. Joni generally has better performance than Java util regex. The implementation there has not really been updated in many years, and this is a much newer, modern implementation of a regular expression engine. And of course, like I mentioned, it has different grammars. There's richer regular expression features, things that you might find useful that you can actually use with Joni, can't get out of Java util regex. And then a cool feature that we added fairly recently, any regular expression engine has catastrophic cases that you can't do anything about. A regular expression engine that will try to match forever. Most developers have run into that at least once in their life. It's just going to continue on. In Java, there's nothing you can do. You've got a stuck thread at that point. You need to reverse engineer, figure out what that bad regular expression was, and why it never finished matching. Well, in Joni, if you do a thread.interrupt on that matching thread, we raise an interrupted exception, you can actually get the thread back and continue on if you've got some bad regular expression. Again, no way to recover from that in Java. And here's an example of constructing a regular expression and searching. API is fairly similar to what you would do in Java util regex, but, whoa, hello then. I can go away now. Let's try that. No? Let's try, oops. Oh, this thing's going all pear-shaped, isn't it? Let's try that. And I can't even push that. Oh, sorry, you can't see that? Oh, it's gone now. Never mind, it was on that TV. Some strange methods. Okay, let's continue on. So, construction and searching. We create our regular expression up at the top. We have the option of using different grammars here. Obviously, I'm just using the Java grammar for regular expressions. We get our matcher out, same as in Java. And then we start searching the string. Down at the bottom, we can see the interruptible version. If we want it to be able to stop executing if it gets stuck in a hard loop somewhere. For dealing with capture regions, groups within the regular expression, these don't end up being copied around. They are simply an array of two integers, where in the bytes that group started and where in the bytes that group ended. So again, no duplication, no copying of character content all over the place. You're working directly with raw bytes, but doing a regular expression match with all the features you expect. It's pretty cool stuff. So performance-wise in Joni, generally what we've seen about 2 to 3 times faster than Java util regex for most loads. This is largely based on our use cases in JRuby, but I think that's pretty good. We're doing very well. The best part, of course, is that if you're working with raw bytes, you don't have to do this transcode step into UTF-16 characters. You can work with the bytes directly as in their original form. And of course, far fewer failure cases. We don't have the Stack Overflow problems. It's a newer implementation of a regular expression engine that supports more features without crashing, without getting stuck. And of course, for the pathological cases, when it does get stuck, you can interrupt it and recover from those cases. Users of Joni, again, Facebook Presto, they use this to do matching against big data that they've read off the wire. Simply not feasible to read all that character data in as UTF-16, so they use our stuff. Nashorn, the JavaScript implementation that's shipped now with Java 8 and higher, they actually did a modified version of Joni that works with regular Java character arrays. So at least they could get JavaScript compatible regular expressions, interruptibility, all of the great features of Joni, but still work with Java strings. We're actually kind of talking on and off about this to possibly put this in as the new implementation of Java util regex in some future version of Java. Grammar support, potential, yes. So we'd like to be able to make a better regex library for Java. This would be a great way to do it. And then again, like I said, the different IDEs that have to support Ruby or have to support multiple encodings use Joni to do matches. I found there's also a plugin that does some scanning and inspection of code for potential problems, uses this library since it might deal with different character encodings across many different programming languages. Okay, so trying to wrap it up here. Some real-world examples. So first one, we've got some data in our database. This is a Postgres database that's storing everything as UTF-8. And we want to be able to translate this out to some ISO encoding, for example. We don't necessarily want to have to read it off the wire all the way into UTF-16 and then back out to ISO 8859-*. So we're going to do it directly. Basic JDBC stuff to get it set up. So here we're going to see how many UTF-8 characters are possible in this column, our string column that we're using. This is a varchar 1000 that I'm using. So we get our size of UTF-8 characters. We multiply that by the size of an ISO 8859-1 character, which in this case turns out to just be 1 byte. If, however, we were doing, for example, shift-JIS, that length might potentially be variable, anywhere from 1 byte up to 4 or 6, I think, can be in shift-JIS. Now we can actually create a buffer that will hold the output bytes directly. So we go into our result set loop. We get the raw bytes off of this column. And now this works appropriately with the Postgres database driver. This gives you the raw bytes off the wire, ideally the representation of the bytes in the database without doing all of that transcoding logic into UTF-16. So we get our raw UTF-8 bytes out. We open up our transcoder, and we can convert those bytes from UTF-8 directly out to ISO 8859-1 without any intermediate step. And then here we do our printing out, and we can get all of the UTF-8 strings, the ISO 8859 bytes, and see what they look like. So the other example here of using Joni. So here we're going to search War and Peace for Pierre and see how many times that shows up in book 1. So we open up our file, and this is actually where I got that example earlier. This is a Windows 1251 encoded file that we want to be able to search without turning it into UTF-16 bytes. I mean, who wants to read all of War and Peace into UTF-16 just to do a quick search, right? So we pull it into raw bytes. We read those bytes in. We get the word Pierre as well, Windows 1251 bytes. Create our regular expression matcher here, and then just walk through the string. Each time we find a match, we increment the count. We found a new instance of this string in the text, increment our index into the bytes, and keep going. And I think this comes out to a couple hundred instances of the word Pierre in book 1 of War and Peace. So, wrapping up here. So, Java string is still evolving. As I mentioned in Java 9, as I mentioned in Java 9, we have a more compact representation. So at least in memory, when you pull in simple ASCII bytes, we're not necessarily taking up a full 2 bytes for every one of those. But largely, we're still kind of stuck with UTF-16 characters for anything that we do with strings on the JVM. I would like to see UTF-8 added as an additional representation inside Java string, so that when we have UTF-8 bytes from the wire, we can read them in and send them back out without the UTF-16 step. That's still kind of debatable. It adds a lot of complexity to the string implementation. I hope this makes it clear, and maybe you folks all realize this already, we live in a multi-encoding world. You can use these libraries to work better in that world. You don't have to force everything through Unicode. You don't have to accept the overhead that Java imposes upon you. And we would like to see folks like you, we're going to continue to work to try and integrate this better with Java string. Maybe someday in the future we'd have a string that can support raw encodings without everybody having to use UTF-16 all the time. And finally, not directly related to character encodings, I think Java util regex kind of needs an overhaul. Those failure cases can be catastrophic. There's no way to do some matches, and there's some expressions that will just blow up the entire thread. Matching on byte could also be added if we didn't update to Java util regex. There's no reason that the engine behind the scenes has to only work with characters. As proven here, we've got a library that can do it against bytes. There's no reason Java couldn't do the same. So I mentioned help wanted. This doesn't need to be like that. There's the URLs for all the projects. Bytelist, being the oldest library we have, has kind of the most cruft in it. It's kind of decayed a little bit over the years. Some deprecated methods over time. The documentation could be improved. We'd like to improve this and make it kind of the canonical tool for using a string buffer of bytes, basically. J-codings, mostly in the documentation area, but if you do start using this, we'd like to hear what sort of performance you get. We're constantly trying to improve it, make sure it runs well, so if you see any issues, let us know. If there's any additional encodings out there, unusual encodings, for example, EBCDIC, the old IBM punch card encoding, if anybody's dealing with any mainframe content, we do not have EBCDIC support right now, but it could easily be added. And then in Joni, again, mostly just interested in what sort of performance cases you have. If you run into any of those pathological cases, maybe there's things that can be fixed in Joni as well. All right, and that's all I've got today. Looks like we got about 5 minutes for questions. Thanks very much.
Друзья, у нас есть еще телеграм-чат, вы туда тоже можете постить вопросы. Вот, если у вас сейчас есть вопросы, самое время их задать.
Hello, thank you. So, as far as I understand, your JRuby strings can contain UTF-8 inside, right? So, what happened when you suddenly changed this white UTF-16 string with UTF-8 string? What happened performance-wise or memory-wise?
One, two, three. So back to me. So what happens, for example, if you have a UTF-8 string and it gets combined, or you call it with a UTF-16 string, or a shift-JIS, or ISO 8859-12. All of the string functions on a Ruby string know how to negotiate those encodings. If it's simply doing a regular expression match, well, we use Joni. We can actually just do the match directly against the raw bytes. Sometimes, if you have two encodings that you're trying to, for example, insert UTF-16 string into a UTF-8 string, well, we will have to transcode it, but that happens transparently behind the scenes. In practice, usually you end up picking one encoding that you use for all of your internal representation, which might be UTF-8, it might be ISO 8859-1, and the translation does not have to happen very often. But JRuby string does take care of all those cases properly.
You just answered for my first question, but I have another one. Could you show the slide with interruption? With regular expression interruption.
Regular expression match with interruption, yes. Yeah, that one?
Could we continue our matching after that? Or maybe you have another way to do this?
Yeah, so you could go back into it and continue matching. So essentially it gives up on the match at that point. You don't have an index where it gave up or something like that. You're not partway through the string. At this point, usually there's two cases. One, the regular expression is bad, and it's always going to do this. Two, you needed to interrupt it simply because, for example, you were matching over much more data than you expected. But in both cases, you can back off and say, okay, something's not quite right. Let's look at that and try it again later.
But the second case, it's not about this. It's about I need more memory or something like this.
Right.
And how can I recover?
Well, so for example, if you ended up reading in too much data, maybe this would be the point at which you break it up into smaller pieces of work. Match over part of the string, for example.
But in this case, on the corners, we can just something miss. In the end or begin of the strings
right.
or parts, you just miss something.
Right, exactly. And so then it would require, so the case would be is if you have a regular expression match that's between two byte arrays. Yes, that's certainly a problem. You can adjust that by saying, I know how long this match should be. I'll make sure that there's enough overlap on the edges of those byte arrays. But yeah, it's messy. I mean, there's not really a good answer for that problem. But this at least lets you try something else.
Are you going to improve this part or not?
Certainly we're willing to make improvements here. The interruptibility feature was just very recent. And for example, it doesn't give you any information about why it failed, whether it was a bad match or whether it was too much data. We can add more of that information here for sure.
Okay, thank you.
Yeah.
Is any plans to migrate your experience for JRuby into Java through GAP or whatever? Because it's really necessary to get rid of that constraint for 16 bits for for Java?
Yeah, that's a good question. So any possibility of getting this into Java? I would love to. The challenge of replacing Java string, as you might imagine, is almost impossible. But there may be things that we can do, like, for example, allowing string to have different representations internally. So at least we're doing a compact, efficient representation of UTF-8, not doing that transcoding. Improving the regular expression engine so it has some of the cases and features of Joni. We have not started any of those processes yet. The first one would probably be to replace Java util regex with Joni as the first step, but adding in more encoding support. Somebody at JBreak in Novosibirsk asked if maybe we should add byte list to Java. Anybody here want to have a nice mutable list of bytes? Well, yeah, every time I use bytes, I want one of those. So yes, there's definitely possibility to start including these in Java in the future.
Thank you.
Dmitry, my name, from Amazon company. You mentioned that Java uses only 14 bits for character representations. And what is the reason to use only 14? And what information are stored in another 2 bits?
Well, so the other bits that are there used for specialized characters that represent, for example, whether it's left to right or right to left language, how you combine characters together if you need to take a diacritical mark and put it above another character. They're also used for marking that we're not just a UTF-16 character. For example, all of emoji, which we all pretty much have to deal with now, cannot be represented in a single Java character. So if you're simply walking through Java strings and looking at individual characters, you're going to break emojis basically in half. That's what those other 2 bits are for. They're used as marker bits for other characteristics of the language.